this stuff with sea level rise is kind of just something I do in my spare time, unfortunately, for now. But with that said, that also means I don't have any vested interest in it one way or the other. I just look at the facts, and I think that's kind of a nice thing to do once in a while. So let's just jump right in. Okay. So what you're looking at here is we've got 20 years of observations made right here on Virginia Key, where I work. And this site is very well established. It's not just something someone decided to install and no one takes care of it. This is a very reliable site. And it has been there for a little over 20 years now. And so what I plot here in the blue line is just the once a day highest high tide value. So there's a lot of noise in it. There's lots of, so this is just the high tide, but of course the low tide would, if I plotted that, would look a lot like this. So yeah, the first thing you notice is there's a lot of noise. There's a few really big spikes that are usually been associated with storms that went by, like here's Hurricane Irene in 1999, Hurricane Rita, and Wilma in 2005. And then one of the highest spikes actually was just last year at the end of September, which wasn't associated with a storm at all. So a routine of the season king tide. So that's kind of an interesting tidbit. The red line on here, I just applied a 90-day mean through the blue line. So you kind of get rid of a little bit of the noise. And what jumps out right away is, we have this once a year peak. It's not always exactly the same, of course, but every year there's a big peak in the fall and a little bit less of a peak a few months before that. So if we go through and average every day for all 20 years, so average all the January 1st together, all the January 2nd together, all the January 3rd together, so on, so on. We can come up with kind of an average of what the tides look like here. And indeed, in September, October, we have the highest tides. This is without anything else happening. This is the tides in September and October are about, on average, 10 inches higher than what they are right now. So that's kind of a good thing to know. That's a rather big range. So yeah, we kind of have that little bit of a peak in May, and then the large peak in September, October. So this is a really good thing to know that you do, under just perfectly normal times, you're going to have a fairly large range in high tides throughout the year. So when you hear about Miami Beach and that floods during the king tide, which is at the highest tides of the year, it'll be in this time of year. It'll be during the full moon of September, October, and November. So these are when the ocean is usually the highest, just because of a certain number of influences that I'm going to take a look at right now. So there's a few things that influence our sea level, of course. We have the phase of the moon. Full and new moons both exert more force on the ocean, which you can kind of see here, that when the moon is in line with the sun, that causes our tides to be more extreme. The highs are more high and the lows are more low. And then the other two reasons that tides change is how close the moon is to us, because it doesn't circle us in a perfect circle. So there are times when it's a little bit closer and a little bit further away, and that matters. So when the moon is close to us, it increases the tidal range. So again, highs are higher, lows are lower. And then also during the year, we're not always exactly the same distance from the sun. Actually, right now, we're about as close to the sun as we'll be all year. So that's one of the ingredients right now that's making our tides a little bit higher than they would be if that weren't the case. I mean, obviously, there's other things that happen during the year, but this is one of a lot of things that influence what the tides do here. So those are kind of the large scale, you know, where things are in space. So what about here? There's a few things, and I couldn't list them all, and I probably don't know what they all are. But a few of the really important ones are the wind. If we have a persistent onshore wind, so wind coming from the east, because the ocean is to our east. So if the wind is consistently strong from the east, that will increase our sea level here. And that could happen over the course of weeks and months, that you could have this abnormally strong easterly wind. Another thing that affects everything is the ocean temperature. If it's warmer than average, it'll expand more than average. The other thing is just the atmospheric pressure. If for whatever reasons the surface pressure is a little bit less than it would be normally a certain time of year, that actually allows the sea level to increase. And then the other thing that matters up and down the whole East Coast is the strength of the Gulf Stream, which is that kind of strong current in the ocean that runs up the East Coast from south to north. And there's a piece of the Gulf Stream right near us called the Florida Current. And that plays actually a pretty big role here. When that slows down, our local sea level increases. And when it speeds up, it can go back down. And over the last few years, actually, the Gulf Stream is not as strong as it usually is. So that's been helping to increase things here and more. So those things I just mentioned, we're going to look at what those usually look like here throughout the year. We're going to look at sea surface temperature, surface pressure, and wind. And they're all going to be kind of in this red area here. So not a huge area, but just kind of what influences would affect us here. And then there's actually there's actually an underwater phone line that runs between West Palm Beach and the Bahamas. And when salt water flows across that, it can induce an electric current. And the strength of that current, you can deduce how strong of an ocean flow there is. So that's really pretty cool. So we'll take a look at that too. First, let's start with just the ocean. This is the sea surface temperature, which is not the best indicator. One of the things I'm still looking for is actually called the ocean heat content, which measures kind of the heat through the depth of the ocean. That would affect it more than just this, but this is kind of a good first look. And not surprisingly, the average sea surface temperature around here is least in the winter and reaches its peak about kind of the end of summer. So no big shock there, right? But one thing I do throughout these graphs is I shade toward a blue where that influence increases our sea level here. So a higher value on here increases our sea level here. So moving on to surface pressure, this is interesting because now we start to see these two humps. And here, where we have less pressure, like I said before, that's where it also can increase things here. So we have a little bit of a hump in May and a little bit in September and October, which is rather interesting, isn't it? Because that's where we saw the other humps in where the average sea level increases here. And likewise for the wind, this is kind of the east-west wind, and values less than 0 are more, they're more out of the east. So this is a light wind out of the east, and this would be more of a wind out of the east. All year long, our wind is on average out of the east. That's why these are always less than 0. But again, you see the two humps again in May and October. So this field also would suggest that we'd have higher, on average, a higher sea level here in May and October. And then the other one I wanted to look at was, again, the strength of the Florida current, which doesn't have as much of a seasonal cycle, but it does have a peak kind of in the mid-summer and a minimum in the winter. And when that, like I said before, when that's less, that's where our sea level can increase. So that's this time of year. So this next plot is a little confusing at first, but let me go through it. These 4 lines, red, green, blue, and orange, those are the same curves you just saw, but now what I did is I scaled them to go just between 0 and 1, where 0 is where they have the least contribution, and 1 is where they have the most contribution. So all of those curves are on here still. And they're just all scaled between 0 and 1. One's not ranked more important than the rest. And then if you average those, all 4 of those into this thick line in purple, that's, again, scaled between 0 and 1. So there's no, I don't rank which of those is more important, and I'm sure one of them is more important, but it's hard to say by how much or anything like that. So this is just a crude look. But what you see is this peak in May and this peak in October. And I'm going to bring back that slide that I showed before of what the actual average values look like. And I think these 4 combined, at least in a crude sense, pretty much account for what we see throughout the course of the year here in when we can expect tides to be at their lowest and when they reach their peak. So that's kind of just an interesting, few things to look at, that why does this look the way it looks? So I thought that was kind of a fun thing to look through. It's always good to know why things are the way why things are the way they are when you're looking at them. So this is going back to that same plot I showed before. This is the once a day highest high tide, except now I just kind of had it grouped into 5-year groups. So there's nothing too special about that. But then what's also plotted on here is just a simple trend line through the past 20 years, through the past 15 years, a little more of a slope there, the last 10 years, and then the last 5 years. And what you notice is that at each time, the slope gets higher and higher. That's a rather interesting thing. Now, these numbers down here are actually what those trends work out to be. This is 0.22 inches per year over all 20 years, 0.35 inches per year, 0.48, and 0.92 inches per year over just the last 5 years. Now, we have to really be careful of how we use this, because first look, I'm going to point this out on the next slide, but I'll mention it while I'm on this slide. This doesn't really work out if you think about it. This would be about 5 inches of sea level rise in just the last 5 years, if that trend were actually happening over the last 5 years. And that's not actually what we observed. So there are issues with drawing just a plain trend line through this, and I'll explain that. So the rates of sea level rise are increasing, but, and a really big but, the trends of a noisy time series have to be used with a lot of caution, especially with relatively short time periods. And here's why. We see it in the 20-year trend. We see the 0.2 inches per year, which is probably pretty reliable, but more years would help. You'd get certainly you would have more years to kind of help get rid of the noise. When you get down to only using 5 years of it, and you get to 0.92 inches per year, I would say that's likely not an accurate number. And let's just think about that. If sea level rose 4 inches in the past 20 years, it certainly didn't rise 5 inches in the past 5 years. So that's your clue that things don't add up with a shorter time period. Although a longer time series allows for higher confidence, you can't account for the accelerating rates. So it's kind of, you have your, you want a longer time series to create a more reliable trend, but then the longer time series you use, you're not able to account for increasing rates because you're stuck to a straight line. So it's hard to say, what length is exactly the best time frame to use. There's no answer to that. So I'm going to look at this in a new way. So this is using exactly the same data, all from this the gauge out here on Virginia Key. But now we're just going to look at an average for a whole year rather than once a day. So now I'm looking at the all the low tides averaged from 1996, 1997, 1998, the mean sea level, and then all the high tides. So there's only one high tide value per year now, and one low tide value per year, and then the mean. So you really get rid of a lot of the noise. And if we draw a trend line through all 20 years, they come out to roughly the same. This is 0.2, 0.22, and 0.23. So an average of those comes out to about 0.22 inches per year. Well, that's really kind of cool, because that's exactly what we got from this 20-year trend line through all the noise. So I think that's a pretty strong number to use, because you arrive at the same answer through two pretty independent ways of looking at it. So that works out to about 4.4 inches of sea level rise in the past 20 years, and I would feel pretty good about that number. Now, what about the more recent times? That's not as easy. And again, there's no answer. There's a lot of ways to look at it. So what I did here, this is the same chart as what's on here. But so what I did to eliminate the year-to-year changes and the dependence on what endpoints you pick, I picked the past five-year trends of each of these time series. So it's an average of 15 trend lines, actually. And as an example of why you don't want to pick just a certain one, let's look at 2011 to 2015. Let's just pick on this curve. This is 2011, the mean, and this is 2015. Well, that's a pretty steep slope, because 2011 was a pretty low year, and 2015 was a little high. So if you draw a trend line through that, it's going to be pretty steep. Well, then let's go back and use the last 5-year period. Then you have the 2014 to 2010, and you draw a trend line through that, and so on. And actually, if you use the 2007 to 2011, okay, now you've got that point, drawing a trend line through that, and including this point. The trend line is actually decreasing in that 5-year period. So it really does matter what 5-year range you're using. So using more than one helps get rid of that problem. So if we average all 5 of these 5-year trends, I get an increase of 0.4 inches per year. And again, that's not an answer. I don't know, not everyone would probably agree with that, but I think this is a reasonable way to come up with a recent trend, not having to use all 20 years, and not relying on just a single trend line through the most recent 5 years. So I think we can say that the recent trend is about twice that of the 20-year trend. That was the 0.22. And over these recent year averages, you get about 0.4. Okay, so now let's use those numbers and some of the other numbers that are being used across the, across South Florida, across the U.S., and across the world for what to expect over the, through 2100. And these two are the numbers that I came up with. If we use this 0.22 inches per year, these are the sorts of numbers we'd be looking at from 2015. So if we look ahead 15 years, that works out to 3.3 inches, and so on, about 19 inches by 2100. And that I kind of added onto this graph. That's this line. This is a single straight line. If we use the 0.4 inches per year, which is the more recent trend that I came up with, not everyone would come up with the same number, but that's this line, and that comes out to about 6 inches in the next 15 years, and almost 3 feet by 2100. And that's just a single straight line. That's just simply taking what the recent trend is and going out with it in time, which probably is not a very realistic way to do it, but I just have it on here for something to refer to and to compare to. The IPCC report, is that something you guys have heard about or looked at?
Yeah.
Yes.
Yes.
Okay, so that's, they have a lot of different curves in that report. This particular chart is one that the Southeast Florida Regional Climate Change Compact is using, which was just written in 2015, as kind of a range of curves that they think would apply most to us. So that's why I'm using this. And for reasons explained in that report, they base everything off of 1992 years, or off of 1992. And there are good reasons for that, even though it seems strange. Like, you know, okay, they wrote this in 2015. Why in the world would they base sea level rise numbers off of 1992? I would encourage you to read the report. It's actually really, really good. So anyway, there are reasons. So all these numbers are based off of that. But if we use the simple 0.22 inches per year trend, sea level has already risen about 5 inches since 1992. So we can subtract that 5 inches from all their lines because we've already had that. So that's what this chart up here, these numbers already account for that. So that's why these don't match up. So here, like for this is the U.S. Army Corps of Engineers. Their report is expecting about 10 inches of additional sea level rise by 2030. But that 10 inches increase is 10 inches from what sea level was in 1992. So when I have it up here, I call it 5 inches because we're already 5 inches into it. So anyway, that's why the numbers in that little chart and the numbers up here don't agree. They're off by 5 inches, and I did that for that reason. And then one of the highest curves, which is what's encouraged to look at when you plan for really major infrastructure, you're encouraged to use the upper end because you're doing something that might, you might begin construction in 15 years, finish construction in 20 years, and it might need to last for, a fairly long time. So you don't want to be stuck, out here when sea level is already up here. So there's kind of a fairly large range. This is really kind of an issue. If you're worried about what sea level is going to be out here, 20, 60, 70, 80, it's a rather enormous range. Even from here, from about 1 to 3 feet. That's a big spread. So why is there such a big spread? Well, there's a lot of sources of uncertainty. Even without man-made effects, the world changes. The globe warms and cools without us. It has been warming before humans were around, and it's warming even more now. But there's things that happen in the natural system that we don't understand completely. The effects of the existing greenhouse gases on sea level is something that we don't understand perfectly well. We kind of have some idea, but not perfectly. And then the further out you go in time, the less you understand. This one is certainly something we don't know. What will future greenhouse gas emission scenarios be? That depends on who's leading this country and other countries and what they can agree on to reduce greenhouse gas emissions. So who knows? That's a complete question mark. What countries will agree to in 25 years? Who knows? Ice loss, we can kind of expect a warmer ocean to kind of melt away at the ice, but when you have enormous pieces of ice shelves lost, or when there's some kind of like an inland sea that might be on an ice sheet somewhere on a pole, if that all of a sudden is released, you could get a really big spike in sea level across the world, and that's not something we know is going to happen at any certain time. And then the other big problem is the climate models that we use have inherent errors that grow with time. You know, they can predict what the climate will be in 5 years a lot more accurately than they can what it will be in 100 years. So all these errors combine, and that's why you kind of have this increase of uncertainty of, okay, maybe it'll be a foot more in 2100, or maybe it'll be 6 feet more. That's actually a realistic spread because there's so many unknowns. But it's the best we can do. These are based on expert interpretation of many of the most trusted models and the most likely climate change scenarios. So what is certain? We do know that sea level is rising at increasing rates. And all of South Florida, and not just us, I mean, places around the world, but all of South Florida is extremely vulnerable to this, both with, you know, not only is the water level creeping up closer to the coastline, and, you know, the coastlines retreat with it, but we also have the saltwater intrusion problem, which you've probably heard about. The other thing is this tidal flooding, which is also called nuisance flooding. It'll become more frequent and affect more areas. So again, if you think of sea level rise being 4 inches higher now than it was 20 years ago, someone that has 4 inches of salt water in their house, those 4 inches are really important to them because 20 years ago they wouldn't have had that, and now they do. A higher baseline sea level will exaggerate the impacts from storm surge and heavy rain events, which is kind of the same point as this, where places that maybe didn't used to flood from some amount of rain, or say there's a hurricane and the exact same hurricane 20 years ago could hit now and flood places that wouldn't have flooded back then. And then these last 2 points are really, really big. Sea level rise is a slow motion crisis. It's hard to get people motivated about it, or even hard to convince some people that it's happening, because it's not something you see from one day to the next or from 1 year to the next. We're talking about a fraction of an inch per year on average, which, you know, we have the range of high to low tides, and throughout the year, high tides vary by a lot. So this is kind of this is all happening in the background, and you only see it in a long-term, when you're looking at the long term. So it's not something that you can just look outside and watch happen, like a strong hurricane or something where people go outside and you can see it happen. This isn't something you can watch happen. It happens over years. But to be able to adapt to it is a long-term, complex, and costly process. So you can't. It can take 20 plus years to adapt to certain things. So you have to start doing it now when it's still something we can work on, and don't wait until it's already a problem. These sorts of things take a very long time to do. And so when you're looking at long-term projects that you have to plan out 25 years, 50 years, now's the time to start them. So with that, I will take any questions, and I really appreciate being invited. And if you guys have any questions about this or anything on like the post or anything, you can certainly get in touch with me. Thank you.
That was amazing. Thank you so much. You can hear us, right? Did you hear us clapping?
Yes.
All right, I have a lot of questions, but I'm gonna let who has a question for you guys? Come on.
What was causing those two separate humps, you think?
Could you please repeat that?
What were causing those two spikes that we were seeing, the large one and the smaller one about a couple months before that?
Oh, okay. Yeah, so those were, so you're talking about this and this?
Correct.
Okay, that was from these. These different things that I looked at, they seem to all kind of, when you add them up, they all kind of create this peak in October and then a little bit less of a peak in May. And that lines really well with this. So I think those pretty much account for why that looks the way it looks.
But Brian,
the sea surface temperature, surface pressure, onshore wind, and the Florida current. To some degree, again, I didn't rank them in terms of which affects it more because I don't think we really know exactly. But this is just when they affect it the most.
Brian, can you go back to that slide? So like, I think it's obvious that sea surface temperature, when it's hotter, there's a higher sea level because the warming water is expanding. But something like surface pressure, can you kind of explain those other things, like how they impact the sea level, like the mechanism, the process?
Yeah, yeah. So yeah, let's just look at this one for now. So we look at surface pressure. Surface pressure is just how much pressure is being exerted on the ground by the column of air above it. So you think of, your place on the ground, and there's this from you all the way up to the top of the atmosphere. There's air, and it pushes down. And the more it pushes down, the more it can depress the surface of the ocean. So a high pressure can actually reduce the height of the ocean. And when you decrease the surface pressure, the ocean can kind of come up a little bit. And you actually see this effect on a much more small scale when you have a strong hurricane. In the eye of a hurricane, where you have a very sharp drop in surface pressure, that's one of the contributions to the storm surge. Most of it is just the onshore winds that push the water onshore. But a piece of that storm surge is actually just because you have such low pressure in the eye. So when the eye comes ashore, you kind of have this bulge of ocean water that comes with the eye. It moves with the eye. So that's kind of how that works. So that makes sense?
Yeah, that really clarifies it. That's so interesting how they're opposite. What about the next one?
Okay, so this is the wind, and this is, like I said, this is kind of the east-west wind. A west wind would be values above 0, and an east wind is less than 0. And all year long, on average, our winds are out of the east, so these are all less than 0. But in May and October, these two times a year, we have the winds are even more strong out of the east. So during these times of year, water is really, you think of just wind blowing out of the east from the ocean onto land. And on the large scale, over these months, you kind of accumulate ocean water onto the land. It can't all just move out of the way right away. The ocean is really kind of crazy. It's not just flat around the world like you might think it is, like perfectly smooth and even. It has high points and low points and all sorts of really cool things. And this is one of the reasons why. yeah, so here on the coastline, because we have a north-south coast here, so it's really pretty nice to look at. It makes it really simple. If we have a west wind, you have wind blowing offshore. And if you have an east wind, it's blowing onshore. And the more strongly it's blowing onshore, the more the ocean level increases here.
Where did
Is
you
that
get the
clear?
Yeah, where did you get the data? Is it NOAA?
Yeah, yeah. Yeah, this is all stuff, if you guys wanted to look at this, you could look at it month by month, or like, so what I did here is I averaged, each month I averaged over these years. So 1981, 2010, I just averaged, you know, all of the Januaries together, all the Februaries together, all the Marches together, and so on. So it's a, you know, it's a pretty robust thing, and but you could look at it one year by year, and there'd be a lot more noise in it, of course. Are there any other questions?
Yes, there are. Come on,
Great.
Lexi.
Why was the Florida current inverted? How is that compared to the rest of them? It looks inverted. Can you clarify that for me?
Oh, yeah. So I mean, so this is the strength of the Florida current throughout the year. It reaches its peak, you know, here in July, and it's as weak as it usually gets all year, you know, about now. Now the reason, what I did on this next plot, so this is scaled, like I said, here when you get into the blues, when the Florida current is weaker, is when sea level increases here. And so these are all put on here so that they're scaled with the maximum contribution to sea level at the top. So the Florida current, when it's at its strongest, is when it has its least contribution to
Oh, that makes sense.
sea level here.
Yeah,
It's like it's going fast.
And then, you know, like the SST, the sea surface temperature, when that is at its highest, that's also when its maximum contribution is. So that's why this one looks inverted. It's just because it's when it's at its weakest is actually when it has its maximum contribution here. Is that clear?
Yes, thank you very much.
Sure.
I have a quick question again about the current. Have you've averaged all of those years together, and all the months together? Has there been a trend, like going from year to year to year to year? Has it been changing, increasing, or decreasing?
That's a really good question. I haven't looked into that too much, but one thing that some people have observed is that in the last probably about 5 to 10 years, the whole Gulf Stream has reduced in strength. The Florida current is kind of just a piece of the Gulf Stream. And so it is actually known that in recent years, the Gulf Stream is not as strong as it usually is. And so that's one of the reasons our sea level is increasing so quickly in recent years. Now, will that continue? That's really hard to say. I don't think anyone could say. But yeah, so that's why that's one of the reasons why this is actually important to look at. And if you looked at this, like you said, 1 year compared to the next year compared to the next year, I think you would see, like, let's just say you looked at 2015 compared to 2000, I think you would see that it's less overall. That maybe 2015 would be down here, and 2000 might be up here. something like that.
I have a question. Do you think the decrease in current has anything to do with the desalinization of the water, like in the Atlantic Ocean, or?
Yeah, I think it probably does. It's probably related to the ice melt off of Greenland. The more fresh water you have melting off of there, that actually reduces the strength of the whole Atlantic Ocean circulation.
Because with the ocean conveyor belt, that's where the salt water should theoretically sink and go down.
Yeah.
And it doesn't sink because it's not dense enough.
Right.
You guys know about the ocean conveyor belt? Should we learn about that?
Yes, that's awesome.
We'll learn about it.
So that would mean that I'm also right.
Yeah,
By
We're-
CO2
we're talking about the carbon impacting it as well, having more CO2 in the ocean, and the temperature,
Yeah,
all of
this is
those things.
California.
Changing the temperature, CO2, it's all changing the way the conveyor belt works. Imagine if it just shut down. Wah, wah.
Yeah, there's
Yeah. Armageddon.
I told you we're really positive in this class. Something that I wanted to point out is that, you know, the mean sea level, you know, we keep saying 1983 to, what is it? It's a 19-year to 1983 to 2001. So can we talk a little bit about why they use that 19-year cycle and why last year was kind of the highest tides in that cycle? Like, we use that 19-year average because of.
Oh, yeah. So yeah, I think so. You're talking about most of the data you look at are all referenced to the. I think it is like 1983 to 2001. Is that what it is? Something like that.
We were talking about it last October. I think you mentioned to me, or you wrote on Facebook, that actually the lowest tide in October was actually higher than mean sea level. So low tide was above the recorded mean sea level that is used, and it's kind of like because it's a 19-year average, and it goes from 1980 to 2001.
Okay, right.
Is really
One
is
that, you know, that's probably due to update, and actually that's part of the reason why 1992 is used as a reference point here, because it's in the middle of the 1983 to 2001 range, which they're currently using as kind of the baseline. So 1992 is right in the midst of that, and that's why that's picked. There will come a time, probably soon, where that 19-year range that they use will shift. So rather than using 1983 to 2001, maybe they'll use, you know, something ending in 2015. I don't know, but it does change once in a while. They just don't update it often because it's a huge pain because they have to change a lot of things. So it doesn't change often, but it is due to change soon, I think.
right, but I think the point is,
yeah, we won't be using that 1983 to 2001 baseline for too many more years, I would guess.
yeah, I was saying that I think the point is that 19-year span is needed to account for all the natural variability, like the decadal cycles and all the orbit.
Yeah.
The fact that we're right now at the peak of that 19-year moving average means that we're going to start to decline with all those natural factors. But then because of the human-induced factors are accelerating, curving upwards, it'll be interesting where there's going to be like a tipping point where the decrease over the 19-year cycle is outweighed by the acceleration.
Yeah. Yeah, it is really important. That's the reason why they use a 19-year period. You have to really be careful with these because there are things that take a long time to happen, and so you wouldn't want to base your average sea level on what it was in 2015, because there's a lot of things that happen over longer time periods that you want to make sure that that's all included in the average. So yeah, that 19-year average at some point will be updated. Like I said, rather than using the 83 to 01, they'll use the 93 to 2011 or something, but at one point, yeah, it'll be time to bring it up to date. And then what happens is, when you look at a forecast of what the sea level is going to be this week, the mean sea level will be more accurate. You're not going to be stuck to what the mean sea level was 20 years ago.
Yeah, I have a question too. Like, go a few slides up, forward. There was one where you said year-to-year variability. Where was that? Maybe the
Here.
next one.
Yeah, in here.
Yeah. So what is the year-to-year variability? Are those the components?
Yeah. Well, it's just when you look at these lines, they aren't. It's not a perfectly increasing line. You have years that are higher, years that are lower. So let's say from 1999 to 2001, if those are the only years you looked at, you'd say sea level was decreasing. So it's really important to look at longer term trend lines, and because it really does matter what years you pick as the start and end point, right? That's like the example that I picked. If you pick on 2011, this point or this point, doesn't matter. If you use 2011 to 2015, your trend is a pretty steep upward trend. But then if you use 2007 to 2011, it's a downward trend. So you have to be pretty aware of what your endpoints are, and to not rely on just a single one. And you want the longer term. So that's why I kind of used, you just kind of use a 5-year range, but don't keep using the same 5 years. So I did, I averaged the 2011 to 15, 2010 to 14. So you're always picking on different endpoints to kind of smooth out that ups and downs.
Yeah, I think that's a really good point because, a lot of the climate deniers will go into they call it cherry picking, where they go into areas where it actually got cold, or sea level went down. So it's really great that you're explaining this because that was the point I wanted to make. There's a book, Dr. Roberts loves it. I think it's called Flying with Maps. You know that book? So you have to be really careful when you're explaining the data. I think you've done a great job of it just by showing us the same exact data in so many different perspectives. It looks different in every single one, but to look at it from all those different viewpoints, you get a much better picture. I like how you do it in inches, because it lets us visualize better than millimeters, but I actually converted 0.22 inches to millimeters, and it was about so 0.22 inches was 6 millimeters, which is kind of double what they say in the literature. That's kind of the number in the literature, but that's looking at a much longer time scale, and it's different methods.
Yeah, I mean, so if you look at the time series from, I think it's Key West or something like that, which is a really long time series. That's nice to have such a long time series, and you get really nice line through it, whatever that works out to. But at the same time, and that's what let's see, where am I here? Yeah, that's this last point. Kind of a pros and cons with it. A longer time series does give you more confidence in the trend line, but then it can't account for changing rates. You know, like this, if you're just drawing a single line, that's great, but what if sea level isn't increasing at a constant rate?
Right, it's important to know the extremes because those matter.
Yeah, and you know, there was one thing I wanted to point out here, which I kind of spaced when I was going through this slide that you mentioned right at the start. Some news places have grabbed onto this, you know, almost 1 inch per year trend, and they use that as if it's truth. Yes, that's what number you come up with if you draw a trend line through the last 5 years. That's a fact. But that's where all these come in. You have to understand what you're looking at. It's not as simple as just, oh, here's a graph, I'm going to use it. You really need to know, to understand what you're looking at. And it does not make sense that sea level rose 5 inches in the past 5 years. I mean, that's the clue right there, that number is not a good number to use. So, you know, that's where I kind of tried to think of a way to, okay, so we want a more recent trend. How do you come up with one? So this is kind of the way I did to come up with a number that I think is somewhat representative of recent trends.
Right, and this, by the way, you guys, so this 0.92 inches was quoted in a New Yorker article, and people have been going crazy. I'm on an email list, a thread of sea level rise experts that were very upset about the article, and I actually connected them with Brian, and like he sorted them out, a few of them. And I also had him talk to and then there's a, tell him about what happened with Commissioner Suarez. He read the New Yorker, this commissioner, you know him? Brian went to talk to him yesterday. Can you tell us about that?
Yeah, they're just curious to kind of get input from people on, you know, as much as they can get on what the more recent sea level rise trends are. And they're aware of this chart and the, you know, the 0.92 inches per year that comes out of the last 5 years. But like most people, they didn't know, you know, if it can be used in a trustworthy way. And that's why, you know, when it's kind of a shame, I guess, that things can be used out of context, because there's plenty of people who don't understand it, but they know how to just look at a chart and say, oh, that says 0.92 inches per year. That's what sea level rise is. But it's not that easy. So yeah, anyway, I did explain to them, you know, that this number is not one to use and why it's not one to use. And I explained this also. I showed this to his office about, okay, if you want a more recent trend, what might it be? And so I gave them this 0.4 inches per year, which, again, someone else might not agree with, but I think it's a reasonable short-term trend to use. And will that trend keep going into the next 5 years? I don't know. That's a trend of recent years. There's no way to know if that can predict the future. I wouldn't expect it would. But yeah, this number and this trend line through 5 years, you have to really be careful with interpreting things. And so yeah, I've ended up having to do a lot more explaining of why this isn't a good number than why this number probably is, the 0.22 inches per year. I'd rather see people use that one and run with it than these, because as I explained in even blog posts, you have to know what you're looking at, and using a trend line through a short time period is not a great idea.
Okay, do you guys have any more questions?
Yeah, a lot of those are linear. Well, do exponential trend lines fit some of the data better or no?
That's an excellent question. Yes and no. Some of the curves, exponential lines do fit pretty well, again, but not with too much more of a correlation coefficient. It's not that much higher than what it is with just a straight line. Again, because of the noise in it. So yeah, you could fit an exponential line to it, and again, you have issues with how long can you extrapolate that into the future. Maybe even less than you could with this. So yes and no. You could fit an exponential to it, and it would fit about as well as what a straight line does.
Can you go back to that last slide that you had that shows all of the trends? Yeah, like NOAA, the Army Corps of Engineers, and I think a couple other ones.
Yeah.
We call this the fat tail, right? Because if you're looking out in your planning horizons, you have more certainty. Like you said, uncertainty increases with time. But a lot of times on this graph, they'll look at the Key West historical and they'll put it out, and it's really, really low. So this is something that we can put that's a more realistic, historic sea level rise without even accounting for ice melt or thermal expansion. When you say, Brian?
Yeah, and in this report, which again I really recommend you guys read, and I have the link to it on my last slide. They don't use this number. They use the Key West number, and I think they say 3 inches. So they use a 3-inch sea level rise between 1992 and 2015. So they say, okay, if you're looking at how much sea level will rise from 2015 on, they say subtract 3 inches from these numbers. But I'm using the 0.22 inches per year because that's what we've observed here, right here on Virginia Key, over the last 20 years. And with that, 1992 to 2015, you get 5 inches. So I subtract more from these numbers than what they do in the report, and that's just me. So when you read this, just, that's something that you'll probably think of, that, hey, he subtracted 5 and you guys are only subtracting 3. Because I'm using this trend line from here, and they're using the 100-year trend line from Key West.
All right, this was amazing. I have one more question. The question is, it's actually in a few weeks we're gonna have our storm week, and your friends Hal and Jay Barnes are gonna be our guest lecturers. You should join us too, because I want you to tell everyone, you said this is your side hobby to do this stuff, so tell us what you really do at UM, at Erasmus. You're hurting.
Oh, okay. So I mentioned I look at kind of like tropical cyclones, hurricanes. In particular, what I'm looking at right now is there's a mission that NASA is going to launch in October of 2016, and it will be able to measure wind speeds over the ocean. So it's kind of a neat mission. And so what it does is you run out 8 little spacecraft that are going to launch, and they'll all be going around the Earth, and they'll look for reflected, or they'll look for where a GPS is up there. the GPS spacecraft, their signals reflect off the ocean, and then these little ones receive that reflected signal. Well, the stronger the wind is, the more rough the ocean surface gets. And so from that, you can deduce how strong the wind is. And then what I'm doing is I can say, okay, well, let's pretend those exist now. We can create what the observations will look like. We can run a hurricane forecast, kind of a whole computer data assimilation, forecast model, all of that. We can run that with these data, with the wind speed, and then run it without them and see what impact having them has on hurricane forecasts. So that's kind of what I've been looking at. It's kind of neat because you get to live in the future.
Isn't that amazing?
That's really cool.
I'm so thankful that you're my friend, Brian. You're the best. It's just been such a huge contribution to have you explain all this stuff to the class, and we really appreciate it. Thank you so much for taking the time.
Oh, my pleasure.
Okay, with that, yeah. Bye. You're all set?
Bye.
Thank you. Have a good night.
You too.